Starting in the 1950s, ships began towing magnetometers back and forth across broad stretches of open ocean, measuring the strength of Earth's magnetic field over seafloor that had never been surveyed this closely. And the readings came back strange. The field over the ocean floor wasn't smooth, and it wasn't a random jumble either. It varied in a pattern. There were long bands where the magnetism read a little stronger, then bands where it read weaker, then stronger again, alternating one after another and running roughly parallel to the great undersea mountain chains we call mid-ocean ridges. Sit with how odd that is. You might expect the bottom of the sea to be a dull, uniform slab, or at worst a patchwork of local noise. Instead, there were stripes, a barcode, printed across the seafloor, lined up with the ridges as if something had drawn it there on purpose. And that is the thing you can't shrug off. Noise doesn't alternate. Noise doesn't line itself up parallel to a mountain range. The sheer orderliness of the pattern was the problem, because order demands a cause. Measurement error couldn't do this. A random scatter of different rocks couldn't do this. Any explanation you reach for now had to answer two questions at once. Why do the bands alternate, and why are they tied to the ridges? To get anywhere, you have to bring in two facts that, at first glance, have nothing to do with each other. The first is about the rock itself. The ocean floor is largely basalt, and basalt is full of magnetic minerals like magnetite. While that rock is molten, it holds no fixed magnetic direction. But as it cools and locks solid, those minerals align with Earth's magnetic field and freeze in place, taking a kind of magnetic snapshot of which way the field was pointing at that exact moment. The record isn't something you can watch happen. It is set, quietly and permanently, the day the rock hardens. The second fact took longer for anyone to accept. Earth's magnetic field is not fixed. Over the deep history of the planet, it has reversed direction, north and south trading places, and it has done this many times over. And crucially, this was established on its own from the geologic record, quite apart from anything on the ocean floor. So now you have two independent pieces, a field that flips and rock that records the field as it cools. Hold those side by side. If there were some way to make fresh rock again and again across a long span of time, then each new piece would capture whatever direction the field happened to hold when it formed. One stretch records it pointing one way, the next records it flipped, the next flipped back again. You would get alternation, locked into stone as a record of time itself. That is real progress. It tells you why the bands could alternate. But notice what it still leaves out. It says nothing about why the pattern is symmetric. And it is symmetric. That is the detail that turns a curiosity into a genuine constraint. On either side of a ridge crest, the stripes don't just alternate, they broadly mirror each other. The sequence running outward one way roughly matches the sequence running outward the other, like a zipper pulled open from the middle. You can't wave that away. A single frozen snapshot in one rock is a fact about that rock. But two matched sequences spreading outward from a shared center line is a fact about a process. Random cooling won't give you a mirror. One-way drift won't give you a mirror. Whatever made these stripes had to build new rock at the ridge and carry it off in both directions at once, so that both sides recorded broadly the same history. The symmetry doesn't just ask for an explanation. It narrows the possibilities down to almost nothing, which brings us to the idea that fits. The proposal was seafloor spreading. Magma rises along a mid-ocean ridge, cools into new oceanic crust right at the crest, and then, as still more magma pushes up behind it, that fresh crust is carried outward, away from the ridge, on both sides. The ridge isn't a scar. It is more like a seam, where new floor is continually made and shouldered aside. Now watch what happens when you run the magnetic story through that process. Crust forms at the ridge during a stretch of one polarity and records that direction. It moves outward. The field reverses. The next crust to form at the ridge records the opposite direction, and it moves outward too, trailing the first. Reverse again, and you get another band pointing back the original way. One band magnetized one way, the next the opposite way, which is exactly the alternation the magnetometers had been reading. And because every band is minted at the ridge and split off to both sides, you don't just get alternating stripes, you get alternating stripes that are symmetric. Alternation and symmetry, the two features that had been nagging at everyone, fall out of a single mechanism together. And here's the part that matters most, the part that separates a lucky guess from something science can actually use. The mechanism didn't only explain what had already been seen. It predicted more. If new rock is born at the ridge and ages as it travels, then the youngest rock should sit at or near the crest, and the rock should grow steadily older the farther out you go. The freshest crust, right at the ridge, should carry the present-day field direction. That is a claim you can go and test, and nobody had to build it into the original puzzle. It is an extra promise the idea is forced to make. So look at what one hypothesis is now doing. From a single mechanism, spreading plus reversals, you get the alternating polarity, you get the side-to-side symmetry, and you get an age gradient marching outward from the ridge. 3 linked predictions, not one. And that is the difference. A mechanism that only ever accounts for the exact thing it was invented to explain is hard to trust. A mechanism that sticks its neck out and predicts several independent things nobody fed into it, is one you can put to the test. If any of those predictions had failed, the whole idea would have been in trouble. That exposure is the point. It's what makes this a mechanism rather than a story. Now, it is worth being careful here, because it would be easy to overreach. The stripes did not on their own prove that continents move. That is not what happened, and it isn't the lesson. There were other lines of evidence, and the stripes were one major thread among several, but they were the thread that helped pull the others together. By explaining both the magnetic barcode and the very construction of the mid-ocean ridge system with one physical process, seafloor spreading offered something the older arguments had never had, a mechanism that made testable predictions about several linked features of the real Earth. For decades, continental drift had been an idea you could take or leave, plausible enough but with no engine underneath it. The stripes changed the terms of the debate. They turned a disputed notion into something you could hold up against measurements and check. That is why an unlikely barcode on the bottom of the ocean earned its place. Not because it was loud or obvious or the single key to everything, but because its geometry, the alternation, the symmetry, the way it centered itself on the ridges, boxed the explanation in so tightly that only a moving, spreading seafloor could account for all of it at once. A pattern that specific leaves no room for hand-waving. It forces you to say exactly how the world would have to work to produce it. And then it lets you go and find out whether you were right.